All right, so we're going to move on to a new section here. So let's say you're staying with 1 foot in the oven and 1 foot in an ice bucket. According to percentage of people, you should be perfectly comfortable. That's from Bobby Bragan back in 1963. And what that's talking about is if we were comparing two proportions, some people might say, hey, well, average it out, it'll be fine. So that's kind of what we're going to be doing in this section a little bit, but not quite as silly as this. So we're comparing two proportions. So what we're going to do is we're interested in making an inference. We're going to make that educated guess for the difference between two proportions. Using the approach, logic, interpretation are same as you're used to doing. We've already been doing this. The only real difference is our standard deviations have changed a bit. So important things about remembering are p hat 1 and p hat 2. First, it's an unbiased estimator of p1 minus p2. So the difference in our sample proportions is an unbiased estimator of the difference of the true proportions. Second, the variance for the difference of our sample proportions is equal to the sum of the two variances. Remember, just like we did before when we were combining random variables, random variable variance only increases. If I'm doing a subtraction, I'm finding the difference, my variance must increase. From that, we also know the standard deviation. We know it's the square root of the variances, or the square root of the sum of the variances in this case. Now, since we don't usually know P1 or P2, that's kind of the whole point of using the samples, we use the sample proportions from the data, and we use those to estimate. So our estimate for our standard deviation, that's really our standard error. And it hasn't changed. It's going to be the standard error for P1 minus P2, or the sample P1, sample P2, is going to be the square root of P hat 1 times Q1, or Q hat 1, all divided by the sample size of the first one, plus P hat 2 times Q hat 2 divided by the sample size for our second one. So when samples are large, the distribution becomes approximately normal. This is one of the things we've been talking about. We like that nice large samples. Normally we want those samples to be at least 30. So p hat 1, the proportion of the first sample of the characteristic of interest, whatever it is we're investigating. How many people think the president's doing a good job? How many people think, ice cream, the chocolate ice cream, best flavor? How many people are obese? Just the proportion of interest. P hat 2, how many in the second sample have that characteristic? N1, total sample size in the first sample, and of course N2, the total sample size of the second sample. Nothing surprising there. Now, we do still have our assumptions and conditions. Now, before we had to check our assumption conditions for our sample. We still do now. We still have to check it, but now we have to check it for each group. And we must make one more condition we have to check. The independent groups assumption. The two groups we're comparing must be independent of each other. And normally we can do this by simply examining the two groups and talking about the differences between them. So let's see how we run this. A confidence interval for two sample proportion. Just like before we did confidence intervals before the hypothesis test, we'll do a confidence interval before we go into the hypothesis test. First, it's just like the last one. The last one, as we recall, okay, the last one we just had p hat plus or minus. Whoa, went off there for a second. Sorry. We have p hat plus or minus the critical value times the square root of p q over n. For our confidence interval, p hat q hat over n. Well, it's the same thing, except now we're doing the difference. So it's p hat 1 minus p hat 2 plus or minus the critical value times the square root of our standard deviation, which is the sum of the variances, or the square root of the sum of the variances. Hypothesis testing is going to be done in a similar manner also. The parameter of interest when we're testing is the difference between the two groups. So that's what we're going to be investigating. We're looking for that difference, which gives us, of course, that's going to be P1 minus P2. And we'll get to pick, usually we'll get to pick which one is P1 and which one is P2. So the null hypothesis, here's a nice thing about this. The null, just like before, the null means there's nothing interesting happening, no real effect happening. Well, if nothing's going on, then there should be no difference between the two proportions. P1 minus P2 should be 0. Remember, in P1 minus P2, this is now the population proportion. My population should be 0. Or in other words, H naught, P1 is equal to P2. Normally we like the subtraction. It's a little easier to picture it that way. Now if we do that, now we have our alternative hypothesis. Now there's a couple different ways it can look. Okay, first of all, P1 minus P2 could be less than 0. That's just the same as saying P1 is less than P2. Or we could say P1 minus P2 is greater than 0, or P1 is therefore greater than P2. But we still have another thing we could be doing. We could just be looking into the possibility that they're different from each other. And that might be as far as we go. So we're just going to say P1 minus P2 is, well, it's not 0. We don't know what it is. We're not making a claim what it is, but it's different. There is a change between proportion 1 and proportion 2. So we're going to still use our z-test. At this point, that's all we've done so far, just our z-test. Our null hypothesis is the proportions are equal. If that's our null, the proportions are the same, then we're going to pool our groups together to find our p. We're going to have a p hat pooled. That's just how many in the first group had that proportion or had that characteristic plus the number of the second group that had it all over the two sample sizes added together. So we get the how many successes in both samples divided by the number of observations in both samples. And we'll get our p hat pooled. We're going to use that to find the standard error of our test statistic. So I want to make sure we come back to this and talk about this. We use p hat pooled to find standard error. We don't use the individual samples, we use the pooled value. And this is what it turns into. So find our z-score, P1 minus P2, because we're looking for the difference, minus 0, because our null hypothesis is there is no difference, so our mean should be 0, divided by our standard deviation, which uses our pooled data. We haven't rejected our null, so we need to be using our pooled data still. Whenever we have data from different sources or different groups, but we think they're the same population, we pool. Remember, our null hypothesis is there's no difference. If there's no difference, then it's really the same population. So let's say we want to try one of these out. We're going to try one of these out.
Good afternoon. After-school tutorials are over for the day. Teachers, please ensure that students have their bus passes. Students, you may be released to the bus link or to the cafeteria for food.
Okay, so we're back still. Okay, would being part of a support group that meets regularly help people who are wearing the nicotine patch actually quit smoking? So County Health Department tries an experiment. They use several hundred volunteers who are planning to use the patch to help them quit smoking. Subjects are randomly divided into two groups. People in group 1, they get the patch and attend a weekly discussion meeting with counselors and others who are trying to quit. People in group 2 also use the patch, but they do not participate in the counseling groups. After 6 months, 46 of the 143 smokers in group 1 and 30 of the 151 smokers in group 2 had successfully stopped smoking. Do these results suggest that support groups could be an effective way to help people stop smoking? That's our question. That's going to give us our alternative hypothesis. Do the results suggest that these groups could be an effective way to help people stop smoking? Well, if they are, then the proportion of people who quit smoking in the support group should be higher than the proportion of people who quit smoking without the support group. Now we're going to pull in some of this information, and we're going to do it on the next slide here. But we need to look at this, and some information on here we know already. We know my first group, okay? Let's see, in group 1, I had 46 out of 143 quit smoking. In group 2, it was 30 out of 151. So we're going to use those numbers again. We're going to come back to those numbers, but I'm going to take this slide away, but that's what we need. 46 out of 143, 30 out of 151, and it was group 2 that didn't get the support group. So let's go ahead. Call this up. P1, I'm going to call that proportion of people who quit smoking with the support group. That's the one that I think should be higher. P2 is going to be the proportion of people who quit smoking without the support group. My hypothesis, we said our null hypothesis is always the same. P1 minus P2 is equal to 0, that there's no difference between the groups. Our null hypothesis for this is very straightforward. There's no difference, so the difference is 0. Or P1 is equal to P2. I like P1 minus P2 is equal to 0. No difference, and there is in words. There is no difference between proportion of people who quit smoking with the support group and the proportion of people who quit smoking without the support group. My alternative hypothesis is that there is a difference, and specifically, we were saying the support group was better. So P1 should be bigger than P2, so P1 minus P2 must be greater than 0. And in words. So our model, well, my smokers were randomly assigned to groups. 143 times 10, that's less than all smokers. 151 times 10, that's less than all smokers, so I've met my 10% test for each group. Group 1 had 46 success and 97 failures. Group 2 had 30 and 121. All those numbers are bigger than 10, so I've met my 10 success and 10 failure. Each individual one of these passed the independence and the success failure checks. It's also reasonable to assume the two groups are independent. I mean, we did assign them independently. They're going to each group. The groups shouldn't really be affecting each other. So I can use a normal model, and I'm going to run a one-tailed test because I did greater than. If I had done not equal, then I'd need that two-tailed test. I did greater than. It's just a one-tailed test. So it's a one-tail, two-proportion z-test for the difference in the two proportions. So let's see what we have here. We said group 1. Oh, said again, come perform it. Group 1. Now, we've passed all our checks. I've named my model. Now I do my mechanics. Group 1 had 143 people in it. And we said it had, group 2, we said it had 151. Group 1, we claimed 46 people quit smoking while using the patch and getting the support group. In group 2, it was 30 people. So my p hat 1, 0.322, p hat 2, 0.199. If I just divide 30 by 151. Now, I still have to pool my data, so I have all my successes pooled. So I'd have 76 successes out of 143 plus 151, so 294. And we divide that and we find 0.259. This class is an arithmetic class. I'm not going to spend a lot of time on how to do these. It's basic fraction division. All right, so we've got to find my z-score. 0.322, so P1 minus P2. P1 minus P2. And then I use my pooled data because I haven't rejected my null hypothesis. I have my pooled data, but my individual samples. If I do this, I find my z-score, 2.41. I want to find the probability of this extreme or more if the null is true. Remember, that's our check. What's the probability of our sample if the null was true? So my p-value is the probability of a z-score being greater than 2.41. It's basically 0.008. Because remember, this is all we've done. And we found this area. And that's it. Oh, I'm sorry, I forgot that I had the graph on here. Well, that's a pretty low p-value, 0.008. So my observed difference is not likely to just be sampling error, so I reject the null hypothesis. There is strong evidence, because it's 0.008. There is strong evidence that being part of a support group can help nicotine patch wearers stop smoking. Now, follow-up, how beneficial is it? This is where I have to do my confidence interval. I can check a 95% confidence interval basically because my value is so low, I can use a 95% confidence interval, which should be okay. But we'll run a 95% confidence interval. I find my difference. A 95% confidence interval is going to give me a critical value of 1.96. The same way we've always done that. We did 1 minus 0.95 was 0.05. We divide it in half because we were just getting this. We find 0.025. We load that in inverse norm, and we had 1.96. Hasn't changed from the last section. Okay. Then, because we've rejected the null, now we get to go back to using the individual p-value of each sample. Because we've rejected the null, we revert back to the sample data to get our standard deviation. In other words, it tells me my difference is between 0.023 and 0.223. I have to interpret this. We ran 95% confidence interval, so we are 95% confident the support group program could raise the proportion of smokers who manage to quit smoking by between 2 to 22 percentage points. It's not that we're 2 to 22 percentage points better, or that's how many points we're better. We're not 2 to 22% better, but 2 to 22 percentage points better. The proportion actually increased by that many points. Now, the thing is, some people are going to look at that and they're going to grab on that 2% and say, well, you know what? This isn't really, money well spent. There's probably other ways we could raise 2% and not cost much money. Other people might look at 22% and say, hey, we need to do this a lot more. This is definitely worth the money. But the best we can say is that the true proportion, we're 95% confident that it's in that range. That's the best we can say. That's just how statistics works. Ain't it great? So, why is there so little precision in that interval? What could we do to improve it? Well, first of all, we could lower our confidence level. We've been talking about that. I can tell you the weather tomorrow is going to be between 40 degrees below zero to 200 degrees above zero. And I'm pretty confident in that. In fact, I'm about 100% confident in that. But it's not very useful. So if I lower my confidence, I'll lower my interval. Second thing, I can increase my sample size. The more people I have in my samples, the better my samples will be. But it's all about balance. We have to balance out the costs. Increasing sample size is going to cost more money. I have to go and ask for more money to do that. Confidence level. I can reduce my confidence so low that, well, what was the point of doing the study? It's a balance, just like you need in the forest. They look for balance in the forest. Right? So let's try another one here. So in December 2012, the Consumer Reports Consumers Union reported on their investigation on present bacteria in packaged chicken. They purchased name brand, Purdue, and store brand chicken in 25 U.S. cities. Laboratory tests found Campylobacter contamination in 33% of the 75 Purdue packages and in 45% of the store brand packages. Does this indicate shoppers would be safer buying the name brand product? So what's my alternative hypothesis? Does it indicate shoppers would be safer buying the name brand product? That's what I'm trying to prove. If they're safer buying the name brand product, that means contamination should be higher in the store brand product. So that's going to help me set my hypotheses. It's going to help me name them. Now, one thing is, when we call this P1 and P2, we have to be very clear people know what we're talking about. We have to tell them what P1 and P2 is. So let's try this. My hypothesis, null hypothesis, I'm comparing two populations. Think about it. So my null hypothesis, and we should label it, I'll call PP is going to be a proportion of Purdue, and PS, my proportion of store brand. Null hypothesis, there's no difference. That Purdue minus store is equal to 0. Now, my alternative can't be that. We talked about that. My alternative has to be based on what we thought. And we thought store brand was going to be higher. Okay, so our null hypothesis in words and symbols, I forgot I had so many words on there. So alternative, store brand minus Purdue would be greater than 0 then. Or just store brand is greater than Purdue brand. The alternative hypothesis, proportion of contaminated chicken, the proportion of contaminated packages of store brand chicken is greater than the proportion of contaminated packages of Purdue brand chicken. So my model, well, sounds like I'm going to have a 2 proportion z-test, but independence. The packages, now, in this case, maybe they're not independent. Packages that are handled improperly at the store could be more likely to be contaminated. That could then end up being delivered to the same store. Random. Well, Consumer Reports didn't actually say it was random, but they are a professional organization. They've been doing this for a while. We're going to hope that they did it. Okay. 10% condition. Well, 75 Purdue and 75 store brand is definitely less than 10% of all packages of chicken. We've easily met that burden. So success, failure. Again, the two proportion z-tests are nice. We get to just use the data they gave us. So in this case, they had 75 packages, 45% of them were contaminated, so there'll be 34. I think it's 33.75, but we'd round that up. The other one, well, then that means how many failures, how many were not contaminated? 41 of the store brand. Now I go to Purdue brand, 75 times 33% contamination, I have 25 contaminated packages. And that tells me I must have had 50 non-contaminated packages. All of those numbers are greater than 10, so the sample is large enough. Now, independent groups. Maybe the groups aren't independent. For all I know, they got these packages at the exact same store. And if they've done that, and the stores are responsible for the contamination, then if they're contaminating one set of packages, they're probably contaminating the other. So I don't actually know the groups are independent. I'm going to hope they are and keep working, but it's possible they're not. So the conditions could be satisfied. Okay, we don't know for certain, but I can't run any other tests for this, so I'm going to run the normal model for the difference of the two proportions. It's going to be a one-tailed because we're specifically saying that the store was higher, not just that it was a different level. So mechanics, well, still my sample sizes. We said it was 75. We had 34 store brand were contaminated, giving us a p-hat 0.45. 3. Our Purdue brand, we said were 75 packages. We said 25 were contaminated, and that gave us a 0.333 for our contamination proportion. Our pooled, so 34 plus 25 divided by 150. We pooled our data. So now we have a statistic we can use for testing our hypothesis. Our testing one, our p-pooled, is going to be 0.393. So we find our z-score, 0.453 minus 0.333, minus subtract 0 from that because that's our mean if we expect there's no difference. We use our pooled data to find our standard deviation. We run it for both samples of 75 and sample of 75, but we're using our pooled data still because we haven't rejected a null hypothesis. Until we reject a null hypothesis, we use the pooled data because we assume there's no difference at this point. So we get a z-score of 1.5. So now I've got a p-value. I need to find my p-value. In this case, I'm looking for the probability that my difference of them would be greater than 0.12. That's the same as saying a z-score of above 1.5, or we get 0.066. Now, and that's what it looked like on the curve. Now, this is not an incredibly low p-value, but let's think about this for a moment. The p-value is where we're saying if we cut in below this, we're going to reject the null hypothesis. And that means we're going to act as though the alternative is true. So in order to make this decision, what would be the cost of accepting the alternative if we start acting on that decision? Well, in this case, it means we might stop buying store brand chicken because we think the store brand is more likely to be contaminated. That is not a decision that's likely to harm people. Okay? So I don't need the lowest possible p-values. I'm not likely to hurt people by following the hypothesis. I might cost someone a little bit of money, but the chicken is a chicken. Eventually, it's just going to end up being rebranded. So in this case, my p-value is somewhat low. I'll reject the null hypothesis. There is some evidence to suggest the proportion of contaminated packages is greater for store brand chicken than for Purdue brand chicken. So I'd like to know more about the design because there were some questions. Were they independent? Was it truly random? We didn't really know that. We had to act on it without knowing it. I'd rather know more about it before continuing too much. The other thing is if I can get a bigger sample, I may be even more confident now. Now, Tyson was also investigated. 56% of their packages had contamination. So now we're going to create a 90% confidence interval based on contamination difference between Tyson and Purdue. So first thing is, the conditions have already been met. We've already said they were met when we did the first part. Tyson was part of the same study, so they've met all the same conditions. So now I want to find my confidence interval. I need the difference between Tyson from Purdue, and that's going to give me our positive value because Tyson was more contaminated, plus or minus the margin of error, which is our critical value, times the square root of our standard error, which in this case, we need to do the sum of the variances to find it. So in this case, 0.56 minus 0.33 plus or minus 1.645 to do a 90% confidence. That's 0.56 times 0.44 divided by 75 plus 0.333 times 0.36667 times divided by 75. So I get a confidence interval between 0.097 to 0.357. I have to interpret this. We have numbers, but what do they mean? Well, I'm 90% confident the rate of Tyson contamination is between 9.7 and 35.7 percentage points higher than the rate of Purdue chicken contamination. So it's not just a percentage increase, it's how many percentage points is it higher. I mean, this is one we talked about in class where we talked about how if someone's making a 10% commission and I tell you someone else makes 10% more, well, that just means 10% times 1.1. Or all we're going to find out is that second person. So if I tell you someone's making 10% more, that's just 10%, 0.1 times 1.1. Or they're only making, oh, I typed in something wrong in my calculator. That second person is only making 11% commission. But if I tell you one person is making 10%, another person is making 10 percentage points more, well, that second person is making a 20% commission. So that one word can make a significant difference in what you've said. So be very careful and notice how you phrase this. We are talking about how many percentage points it is higher, not how much percentage it is higher. Right? Like I said, it might be a little tough concept. We're going to practice some more. More practice, we'll get a little better at it. So we can also run a two proportion z-test using the calculator. First thing is, we're going to go to stat. We're going to go to tests. And we'll go to a two-prop z-test. Now, when we go here, it's asking us for our samples x1 and x1. x1 and n1. These need to be whole numbers again. x2 and n2, how many successes out of our second sample? We need to be smarter than our calculator. And in this case, we want greater than P2. Or P1 should have been greater than P2. That's what we were claiming. P1 was greater than P2. So here's my store brand, and here's my Purdue brand. And if I run that, that might be a little tough to see that. Let's see if we can make that a little nicer to see. No, it's been a little difficult. Some of it's moved over a little bit. It gives us the same z-score, 1.5, and it gives us the same p-value, 0.066. But if we did the draw, and this is what option I was running the calculator, it actually draws a curve for us and shows us the shaded region. Shows us it did a one-tail test. Or I can do it as calculate. So if I'd run it as a calculate, this is the output I'd have gotten. It's the same output. It's just which one do you prefer? Personally, I like both of them. The draw may be a little bit better in simply that if you're going to be doing an FRQ and so you want to show me what your normal curve look like, you can use draw. So now I need a two proportion z confidence interval using the TI-83 or the 84. So we're still going to go to stat, we're still going to go to test, and we scroll all the way down to my two proportion z interval. When I do that, I've put in my data. Now, if I've run the confidence test, it already has my data for me. I tell it how confident I want to be. In this case, I said 80% because it's a one-tailed test. So if you go back and look at the previous chapter, you can see how we find those values based on our alpha levels. So I'm still going to run a 0.018 all the way up to 22 percentage points. We're still getting the same data, just a little different. If I run two prop z-test at a 90% confidence level, now I'm getting a negative 0.1. I'm getting a negative rate. And all the way up to 25 percentage points. So what that's telling me is if I go to 90%, remember my p-value, let's pull it back, our p-value was 6%. Well, if I increase my confidence too high, I'm going to end up catching 0 inside of my interval. If I catch 0 inside of my interval, then how could I possibly reject it there being no difference? So our warning here is don't go too high in your confidence level. So we have to be aware of that. We can't go too high in our confidence level. So we had some classwork we started on this one. We then finished on into the homework on this one. Hope this helped out a little bit. Ask questions though. Kept up with the notes. And I look forward to seeing everyone later.